Okay, so here we have a problem with a ladder leaning against the wall. No friction on the wall, friction on the floor. This is a classic physics problem where we need to see, does the ladder slip? And then this one also asks, what is the net force at point A? So we will start out here by drawing our free body diagram. And basically what we're going to have to do is sum up our forces in X and Y and sum up moments. Solve for all of the forces at B, the forces at A, and then we can get total force at A. So we will start with step one, which is drawing our free body diagram. So if we have our ladder here, and then this is point B, this is point A, we know that coming from the ground, we'll have a normal force. We'll call that NA. And then up at point B, we've got a normal force from the wall. We'll call that NB. We also have the weight of the ladder pointing down, and we'll put that smack in the middle. We'll say mg, and we are given the angle of the ladder, theta, and then friction force. So if this ladder is trying to slide down the wall, B is trying to move down. It's not a force, it's just a velocity. There's no friction on the wall, B. B is trying to move down, which means A is going to try to move to the right. And the friction on the ground has to oppose that motion. So we'll draw in our friction force pointing to the left. All right. So now we can sum up our forces. Oh, actually, we need a coordinate frame. So we'll say that we have X going to the right, Y going up. So that was step two. And now we need to sum the forces. So we'll start with summing up. So we'll start with summing up the forces in the Y direction. We can get the force at A, and then from A, we can find our max friction. So we'll say sum of the forces in the Y direction equals 0. And this normal force at A has to oppose the weight. So we have NA pointing up, mg points down, normal force at A equals mg, which equals 30 kilograms times 9.81 meters per second squared. And then normal force at A equals 294 newtons. Okay, so that's part one. That's not total force at A because we still have to get friction, but this is one of the forces at A. Now we can find max friction. So max friction equals the coefficient of friction times that normal force. And our coefficient friction here is 0.5. So we have 0.5 times 294. And so this gives us that the friction is 147. F equals 147 newtons. And note that that is the maximum. So we have to figure out the force at B because friction also counteracts B. And if the normal force at B is greater than the friction force, then the block could slide or the ladder could slide. If the friction force, if the max friction force is greater than the normal force, then there won't be any motion. So to find that force at B, we actually have to sum the moments around point A. So we'll say sum of the moments around point A equals 0. And then we have the weight pulling down, and that's a counterclockwise. So mg times its distance, which is, it goes halfway up here. So that's L over 2. But then we actually need this horizontal distance. So that's L over 2 times cosine of theta. So we need the horizontal distance because the mg is a vertical force, and we need force times its perpendicular distance. So the mg L over 2 cosine theta. And then the moment caused by B goes in the other direction, minus normal force at B times its distance, which is going to be L, times this total height, L sine theta. So this is L sine theta, that height right there. So now, let's see, it ends up not mattering really how long the ladder is, as long as the weight's acting in the center of it. We can rearrange this, and we get normal force at B equals to, let's see, mg cos theta over sine theta, which really is mg over tan theta. And we can put numbers into that. In B equals 30 times 9.81 over the tangent of 60 degrees. And in B equals 85 newtons. Okay, so we've got the normal force at B, we've got our max friction force, and we've got the normal force at A. Or, yeah. Okay, so in order to find does the ladder slip, we have to compare friction to normal force at B. Basically, is the friction large enough to counteract that normal force at B and hold the ladder in place? Or is it too small and it slips? So we'll say friction compared to normal force at B. And our friction force is 147. We'll say here max F. Friction is 147 newtons, and the normal force at B is 85 newtons. Max friction is greater than the normal force at B, and so no slip. Now, if each problem will have different numbers in it. So if we did this comparison and the max friction force was less than the normal force at B, then in that case, the ladder would slip because friction is not enough to keep it holding against the wall. And for the net force at A, we have to account for the friction force and that normal force. And so we will need to get the hypotenuse of this triangle, and that distance is total force at A. But which friction force do we use? The max force or the normal force? Well, in order to keep the system in equilibrium, the friction force just has to oppose the weight. So we'll say here for part B, use minimum friction force for balance. Sum of the forces in X equals 0 equals normal force at B pointing left minus the friction force at A. Normal force at B points right, friction force points left. And this is the real friction force. So this gives us that F equals NB, which equals 85 newtons. And this is the true value, because it didn't need to be its maximum. If it was greater than the normal force at B, it would actually push the ladder against the wall, and we all know that doesn't happen. Okay, so what we have to do here now is say total force at A equals the friction force squared plus the normal force squared, square rooted. And we're using minimum friction force for equilibrium. So this tells us we have 85 squared plus the NA, which we got back up at the top, was the 294 squared. So plug those into a calculator and we get 306 newtons equals FA. So this is the answer for part B.